Mandelbrot's fascination with the visual side of math began when he was a student.
It is only in January '44 that suddenly I fell in love with mathematics. And not mathematics in general, with the geometry in its most concrete, sensual form. That part of geometry in which mathematics and the eye meet. The professor was talking about algebra, but I began to see in my mind geometric pictures which fitted this algebra. And once you see these pictures, the answers become obvious. So I discovered something which I had no clue before, that I knew how to transform in my mind instantly the formulas into pictures.
It was 1958. The giant American corporation was pioneering a technology that would soon revolutionize the way we all live: the computer. IBM was looking for creative thinkers, nonconformists, even rebels. People like Benoit Mandelbrot.
In fact, they had cornered the market for a certain type of oddball. We never had the slightest feeling of being the establishment.
Mandelbrot's colleagues told the young mathematician about a problem of great concern to the company. IBM engineers were transmitting computer data over phone lines, but sometimes the information was not getting through.
They realized that every so often the lines became extremely noisy. Errors occurred in large numbers. It was indeed an extremely messy situation.
Mandelbrot graphed the noise data, and what he saw surprised him. Regardless of the time scale, the graph looked similar. 1 day, 1 hour, 1 second. It didn't matter. It looked about the same.
It turned out to be self-similar with a vengeance.
Mandelbrot was amazed. The strange pattern reminded him of something that had intrigued him as a young man. A mathematical mystery that dated back nearly 100 years. The mystery of the monsters.
The story really begins in the late 19th century. Mathematicians had written down a formal description of what a curve must be, but within that description there were these other things that satisfied the formal definition of what a curve is, but were so weird that you could never draw them, or you couldn't even imagine drawing them. They were just regarded as monsters or things beyond the realm.
They're not lines. They're nothing like lines. They're not circles. They were like really, really weird.
The German mathematician Georg Cantor created the first of the monsters in 1883.
He just took a straight line and he said, I'm going to break this line into thirds, and the middle third I'm going to erase. So you're left with 2 lines at each end. And now I'm going to take those 2 lines, take out the middle third, and we'll do it again. So he does that over and over again.
Most people would think, well, if I've thrown everything away, eventually there's nothing left. Not the case. There's not just 1 point left. There's not just 2 points left. There's infinitely many points left.
As you zoom in on the Cantor set, the pattern stays the same, much like the noise patterns that Mandelbrot had seen at IBM. Another strange shape was put forward by the Swedish mathematician Helge von Koch.
Koch said, well, you start with an equilateral triangle, one of the classical Euclidean geometric figures, and on each side I take a piece and I substitute 2 pieces that are now longer than the original piece. And for each of those pieces, I substitute 2 pieces that are each longer than the original piece. Over and over again.
You get the same shape, but now each line has that little triangular bump on it.
And I break it again, and I break it again, and I break it again. And each time I break it, the line gets longer.
Every iteration, every cycle, he's adding on another little triangle.
Imagine iterating that process of adding little bits infinitely many times. What you end up with is something that's infinitely long.
The Koch curve was a paradox. To the eye, the curve appears to be perfectly finite. But mathematically, it is infinite, which means it cannot be measured.
At the time, they called it a pathological curve. because it made no sense according to the way people were thinking about measurement and Euclidean geometry and so on.
But the Koch curve turned out to be crucial to a nagging measurement problem: the length of a coastline. In the 1940s, British scientist Lewis Richardson had observed that there can be great variation between different measurements of a coastline.
It depends on how long your yardstick is and how much patience you have. If you measure the coastline of Britain with a 1-mile yardstick, you get so many yardsticks, which gives you so many miles. If you measure with a 1-foot yardstick, it turns out that it's longer. And every time you use a shorter yardstick, you get a longer number, because you can always find finer indentations.
Mandelbrot saw that the finer and finer indentations in the Koch curve were precisely what was needed to model coastlines.
He wrote a very famous article in Science magazine called "How Long is the Coastline of Britain?"
A coastline, in geometric terms, said Mandelbrot, is a fractal. And though he knew he couldn't measure its length, he suspected he could measure something else: its roughness. To do that required rethinking one of the basic concepts in math: dimension.
What we would think of as normal geometry, 1 dimension is the straight line, 2 dimensions is, say, the box that has surface area.
And 3 dimensions is a cube. But could something have a dimension somewhere in between, say 2 and 3? Mandelbrot said yes. Fractals do. And the rougher they are, the higher their fractal dimension.
There are all of these technical terms like fractal dimension and self-similarity, but those are the nuts and bolts of the mathematics itself. What that fractal geometry does is give us a way of looking at, in a way that's extremely precise, the world in which we live, in particular the living world.
Mandelbrot's fresh ways of thinking were made possible by his enthusiastic embrace of new technology. Computers made it easy for Mandelbrot to do iteration, the endlessly repeating cycles of calculation that were demanded by the mathematical monsters.
The computer was totally essential. Otherwise, it would have taken a very big, long effort.
Mandelbrot decided to zero in on yet another of the monsters, a problem introduced during World War I by a young French mathematician named Gaston Julia.
Gaston Julia, he was actually looking at what happens when you take a simple equation and you iterate it through a feedback loop. That means you take a number, you plug it into the formula, you get a number out. You take that number back to the beginning and you feed it into the same formula, get another number out, and you keep iterating that over and over again. And the question is, what happens when you iterate it lots of times?
The series of numbers you get is called a set, the Julia set. But working by hand, you could never really know what the complete set looked like.
There were attempts to draw it, doing a bunch of arithmetic by hand and putting a point on graph paper.
You would have to feed it back hundreds, thousands, millions of times. The development of that new kind of mathematics had to wait until fast computers were invented.
At IBM, Mandelbrot did something Julia could never do: use a computer to run the equations millions of times. He then turned the numbers from his Julia sets into points on a graph.
My first step was to just draw mindlessly a large number of Julia sets. Not one picture, hundreds of pictures.
Those images led Mandelbrot to a breakthrough. In 1980, he created an equation of his own, one that combined all of the Julia sets into a single image. When Mandelbrot iterated his equation, he got his own set of numbers. Graphed on a computer, it was a kind of roadmap of all the Julia sets, and quickly became famous as the emblem of fractal geometry. The Mandelbrot set.
It's not easy to describe the Mandelbrot set visually. It looks like a man, it looks like a cat, it looks like a cactus, it looks like a cockroach. It's got little bits and pieces that remind us of almost anything that you can see out in the real world, particularly living things. So it has a character that reminds us of a lot of things, and yet it itself is unique and new.
The
Mandelbrot set is real, an absolute thing, no question whatsoever. Any mathematician or any computer scientist or student in a school can study it and find the same, describe the same thing. It's a common experience. And so such things that can be magnified forever and have infinite precision do exist, but they're not touchable.
It's a geometrical shape, an icon, if you wish, which somehow embodies as an example a very important aspect of how the world works. Somebody recently actually called this set the thumbprint of God.
With this mysterious image, Mandelbrot was issuing a bold challenge to long-standing ideas about the limits of mathematics.
The blinders came off, and people could see forms that were always there, but formerly were invisible.
The Mandelbrot set was a great example of what you could do in fractal geometry, just as the archetypical example of classical geometry is the circle.
When you zoom in, you see them coming up again, so you see self-similarity. You see, by zooming in, you zoom, 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 you're zooming in, you're zooming in, and pop. Suddenly it seems like you're exactly where you were before, but you're not. It's just that way down there, it has the same kind of structure as way up here, and the sameness can be grokked.
Now we'll begin our serious exploration of the Mandelbrot set, a voyage which in fact could last forever and ever, much longer than the lifetime of the universe. I have here the full set, about 6 inches across. Now, if I blow this up, I'll increase the magnification now 13 times, and you'll see more and more detail is appearing. And the interesting thing is you see mini Mandelbrots, replicas, almost identical, yet perhaps subtly different, of the original set. And I can go on doing this. Here's a magnification of more than 3,000 times. So the original picture, about 6 inches across, is now half a mile across. And no matter how much we magnified it, a million times, a billion times, until the original set was bigger than the entire universe, we would still see new patterns, new images emerging, because the frontier, the M set, is infinitely complex. And when I say infinitely, I really mean that. Most people, when they say infinitely, they mean only rather big. But this is really infinity. What is so remarkable, in fact astounding, about the Mandelbrot set is that although it's infinitely complex, it's based on incredibly simple principles, unlike almost everything in modern mathematics. In fact, anybody who can add and multiply can understand the principles on which it's based. You don't even have to subtract or divide, still less use logarithms or trigonometrical functions to comprehend how the Mandelbrot set is created. In fact, in principle, it could have been discovered any time in human history and not merely in 1980. But the problem is this: although it's only based on adding and multiplying, you have to carry out those operations millions, billions of times to create a complete set. And that's why it was not discovered until the era of modern computers.
There's an interesting parallel with the equation that almost everybody is familiar with, the only equation almost everybody is familiar with, E equals mc squared, Albert Einstein's equation that says matter and energy are equivalent to each other. That was a very simple equation with very far-reaching consequences. And the equation for the Mandelbrot set is equally simple. Z equals z squared plus c.
The letters in the Mandelbrot equation stand for numbers, unlike those in Einstein's equation where they stand for physical quantities, mass, velocity, energy. The Mandelbrot numbers are coordinates, positions on the plane, defining the location of a spot. Another difference from Einstein's equation, and a very important one, is this double arrow. It's a kind of a two-way traffic sign. The numbers flow in both directions, constantly feeding back on themselves. This process of going round and round a loop is called iteration. It's rather like a dog chasing its own tail. The output of one operation becomes the input of the other, and so on and on and on. When the Mandelbrot equation is given a number representing a point, and that number is iterated through the equation, one of two things happen. Either the number gets bigger and bigger and shoots off to infinity, or it shrinks to zero. Depending on which happens, the computer then knows where to draw a boundary line. So what we get from this basic iteration is a kind of map, dividing this world into two distinct territories. Outside of it are all the numbers that have the freedom of infinity. Inside it, numbers that are prisoners, trapped and doomed to ultimate extinction. Now look what's happening. At the tip of each hair, it splits into two others, and so on. Each is splitting, going on indefinitely. This splitting up, this bifurcation, going off into apparently random directions quite abruptly, is typical of a class of mathematical entities called fractals. The Mandelbrot set is the most famous fractal.
The word fractal means any geometrical structure that has detail on all scales of magnification. No matter how big you make it, you still see extra new details you didn't see before. And the name was actually invented by Mandelbrot himself. He felt he had to have a name for this area he realized he was working in. And so he coined the term fractal because it conveys this feeling of fragmented, broken, fractional, irregular.
A common characteristic of fractal systems is branching. Trees, circulatory systems, and rivers, for example, all display branching fractal patterns.
There are lots of fractal systems within the body. In my work on the heart is actually full of fractals. The most famous example of it is the blood vessels coming into the heart. The coronary circulation is a pattern of a branching network of blood vessels that's typically fractal, where the branching structures look very similar at different scales.
Even snowflakes, known for their dissimilarity from each other, display a fractal pattern internally.
Fractals are shapes which we are extraordinarily used to in, our subconscious, ill-organized life. For example, everybody knows that if you take a map of Britain on a small school globe, you see a very simplified shape. Cornwall is just a kind of triangle, and Wales perhaps a little rectangle. You cannot put the details on a small map. If you look at in a larger map, you add more detail. The closer you come, in a certain sense, imagine yourself like somebody coming on a rocket. From far away you see very little, and the closer you come, the more detail you see. If we come very, very close, you begin to see rocks, and finally the idea of coastline disappears, because one doesn't know any longer where is land and where is water. So indeed arose in my mind to put together a geometry based upon many known facts in mathematics, scattered facts in mathematics, many scattered facts in our experience, many scattered facts in the results of what scientists had done of various kinds, all kinds of putting together all these things and using them as bricks, if you will, of a new building, which is a new geometry.
Living creatures seem to be complicated structures produced from simple rules, simple laws of physics and chemistry. And a lot of the structure that you see in living creatures is organic but pattern structure. Leaves on trees, ferns particularly, things like that, have the same feature that the Mandelbrot set has of you look at little pieces of them and they have lots and lots of detail. And in fact the little pieces look very similar sometimes to the whole thing. It's very tempting to compare the way a simple formula produces a complicated Mandelbrot set with the way very tiny things in nature produce complicated organisms. And there are certainly some similarities in that there is the same kind of unfolding of a process. The instructions are there, but not an actual description of the object.